Hi class, good morning. Let's continue with our lectures on quantum mechanics. Again, our reference is Introduction to Quantum Mechanics by David G. Griffiths. And again, I recommend you to buy this book. It's worth it. So for today, we'll proceed immediately with linear transformation. So if you have a vector in one coordinate system and you want to transform, or you want to transfer that vector into another coordinate system, or you want to see that vector in another coordinate system, what you do, what have been done to that vector is it is transformed. So it's there's an operator that transformed the vector, and this is denoted by this uh, this one here, the t. And the t, the transformation, that is by the way a linear transformation. Let's look at the property later, but that transformation takes the vector in a vector space and transform it into another vector, this one here, this one here. And that is a linear transformation. It is following this is following this one here, the this is following the expression in 3.29, that a transformation transforms a vector alpha times a scalar a plus a vector beta times a scalar b, and that is just equal to the scalar a times the transformation on the vector alpha and the transformation on the transformation on the vector beta. By the way, the t here has a hat here, like this. Sorry that the figure is not showing it. So that's for any vector alpha and beta. So the transformation is not because the components of the vector in the previous uh, space is the original E1, E2 until AN. The n there is the dimension of the space. So in the new coordinate system, the E1, E2, and En, and of course until En, will have to be transformed also by the same linear transformation. And this is it. So E1, this transformation is you have a transformation on the first element, transformation of the second element of the basis of the space, until the transformation of the nth element. And this transformation is done by each element of the basis. So more compactly you have this transformation in equation 3.30. So you can J can be 1, 2 until n, and this part here will just be the summation of that part. I mean this part, where J is equal to 1, 2 until n. So for any arbitrary vector alpha, you can write it uh, in terms of the original basis in a vector in a in an original um, basis. So when you transform it, you have to transform the alpha by applying the operator t here. So when you apply the operator t, each alpha here would have a1, a2, the coefficients will just come out, and it transforms the vector here, ej. And so ej is of course this one, the tej. The tej would just be this one, and this one will be replacing this term, so that you will have this term, and then this term will just give you this. By the way, the summation can interchange. They are commutative, so no problem with that. So that this will uh, this will be an equivalent expression for this, and so that instead of transforming the ej, you have transformed the aj. So instead of transforming the basis vectors e1 until en, you have transformed the components. And so the transformation has transformed the components also into this, to that. So so this is now the elements of your transformation. There are n square elements of the transformation. So if you're transforming a vector that is three-dimensional, then the transformation will contain 9 elements. So if the basis is orthonormal, as I've said in the previous lecture, orthonormal means when you get the inner product of the rows of the I mean, if you have of you have the basis, if you get the inner product from one element of the basis to another element, that would be 0. That's one of the conditions of orthonormality. And if you dot or they get the inner product of the basis with itself, I mean an element of the basis with itself, that would give you 1. So that's what you call orthonormal. So if you do that with the basis with another basis, I mean an element of a basis to another element, that's 0. If you dot it with itself, it should be 1. So that's the orthonormality condition. So the the transformation contains n square elements, and the n square elements are arranged such that it looks like a matrix that's looks like this. So you have the first element t11 in the first row, t12 the second element until t1n, and then you have the second row t21, t22 until t2n, and then you can follow through the nth row with starting with the element t and 1. So um, So if you talk about transformation of vector alpha, or a vector with components a1, a2, uh, an until an, then you are actually looking into a transformation that is in matrix form. And so if you have um, two transformations, for example S and T, then um, the sum of the transformation is the transformation of the sum. Um, if you like, maybe you're confused, but if you are acting two transformation on a vector, acting the sum of two transformation of a vector, then that's just equivalent to uh, one transformation acting on the vector plus the other transformation acting on the same vector. Or if you do that in matrix, you have the sum of the matrix as U equals to S plus T, where U is um, the combined or the sum of the S and T there. So the elements there is also the sum of the respective elements of S and T. That's what it says in equation 3.38. Also, for the product of two linear transformation S and T, the net effect would be first, um, this is for example, you are transforming alpha into alpha prime. That is just equal to the alpha prime would just be equal to um, t alpha, t hat alpha. And if you transform that into a alpha double prime, which is just s hat times alpha prime, that's equal to um, s hat times t hat on alpha. So that's just equal to this equation. So therefore, st uh, in this case is represented by uik. Sij tjk is represented by uik. So you have uh, a transformed twice, first by t and second by s. That's just equal to this expression. So it's kind of long. If you have a vector that is if you have a vector that is multidimensional, the dimension is is a large number, and the calculation would be very long. It will be manageable until the fifth dimension, but when you go beyond that, it's already very um, tasking or taxing. Um, we have U representing the product of the two matrices. This is just UIK, and this is just equal to SIJ TJK. This is just ordinary product of two matrices. So I'm sure that you know how to multiply, or you can just follow this rule. If you want to multiply two matrices, just follow that rule. When you multiply, um, uh, be very careful, because it sometimes in a blink of an eye you'll be lost with the addition. So anyway, um, practice multiplying matrices, because in this particular topic, um, you're dealing with matrices, and multiplication, transpose, conjugation of matrices are are very important to take note of. Um, there's also usually in transformation, and the transformation matrix is actually represented. Most of them are represented by mm, square matrices, or meaning you have matrices with number of rows equal to the number of columns. So usually that's the transformation that we have. But there are also other matrices like this. This is a column matrix in which vector can be written. The vector can also be written as a row matrix, or in this case, it's written as a column matrix with components A1, A2 until AN. So this is representing alpha, representing the vector alpha. So the n tuple of components of alpha can be written as an n by 1 column matrix. That one there. And the transformation, of course, is um, the transformation uh, is just the product of the T, which is the matrix representing the transformation T, and A, representing the matrix representing alpha. So there are several terminologies that we have to study about matrix. One of them is the transpose of the matrix, and this transpose just converts the original matrix into a matrix whose columns are the rows of the original matrix, or whose rows are the columns of the original matrix. So if you have this original matrix here, the transpose would just be, in this case, you have T11 here, and then T21 until Tn1 to the bottom. This will become the row of the transpose. That will be the row of the transpose. So this one becomes the row of the transpose, and then this one will become the second row, and then this one will become the last row of the transpose. So that's how you get the transpose of the matrix. So in an example, or in a problem um, uh, that we will encounter later, you can do experiments or do calculations on how to get the transpose of the matrix. In this matrix representation of the column matrix, the transpose would just be a row matrix. So this is the transpose of the row matrix. This one here, that one. Notice that the transpose has a tilde in the on the top of the letter. That has a tilde on the top of the letter, like this one. It has a tilde. There's a tilde at the top. So now there's a definition here of a square matrix that is symmetric. So if you have a symmetric matrix, then its transpose is equal to the original matrix. So that's a symmetric matrix. There's also an anti-symmetric um, matrix, and this anti-symmetric matrix will just give you a reverse sign of the original. So here, for the symmetric matrix, you have the transpose equal to the original matrix, and then the antisymmetric matrix will just be the transpose as equal to the negative of the original matrix, meaning the sums of all the elements are uh, opposite to the original. So there's also what we call complex conjugate of the matrix. The complex conjugate of the matrix will just be this one. This is the original matrix. Is this matrix here? This is the original matrix. This is the original matrix, and the complex conjugate would just be this one, meaning the complex conjugate would just be uh, substituting all the I into negative I, all the negative I into I. So if you have 3 plus 4I in the original matrix, then the complex conjugate of that would just be 3 minus 4I. Or if in the original matrix you have e to the ix, the complex conjugate of that would just be e to the if the original has e to the negative ix, then the conjugate of that will just be e to the ix. So you just change the sign. So if the real matrix, if you have a matrix that is real, then the conjugate of that matrix would be equal to the original, the complex conjugate, or say you just say conjugate is complex conjugate. And if you have a purely imaginary matrix, then the conjugate of that matrix is equal to the negative of the original. Pure imaginary. If it's pure real, the conjugate will just be equal to the original matrix. Uh, it's a combination, then of course the conjugate will also be a combination. The Hermitian conjugate of matrix, this is indicated by a dagger beside the matrix. That is the Hermitian conjugate would be the transpose, the conjugate and transpose of the original matrix. So here, the rows become columns like that, and then the columns become rows. But in addition to that, you have a conjugate of the matrix. So there's another definition: Hermitian or self-adjoint. Um, um, the matrix is Hermitian if um, if the original is equal to the Hermitian conjugate of the matrix. Hermitian conjugate. And it is skew Hermitian if the original is equal, if the Hermitian conjugate of that matrix is equal to the negative the original matrix. So it's a definition. And we now, with this notation, the inner product of two vectors with respect to orthonormal basis, you can write it in matrix form. So this is the inner product before, and now that you know that they are composed of components, then you can write the inner product to be in in the form of matrix. The Hermitian conjugate times the other vector. And we do matrix multiplication, by the way. In general, the matrix multiplication is not commutative. It's not commutative, meaning that the matrix, the two matrices S and T, when you multiply that in that order, is not necessarily equal to T times S, or S multiplied to T is not necessarily equal to T multiplied to S in general. But there are also matrices that are equal, but there are special cases. And by the way, we have this kind of notation S comma T here enclosed by square bracket. This is equal to ST minus TS, because most of the time ST is not equal to TS. Um, and if they are equal, then this one is zero, meaning if they are equal, the S and T and the S multiplied to T and T multiplied to S, if they are equal, both of them are the same, then we say that the two matrices are commutative. And hence their commutator will be zero. So in general, this is not zero. In general, this is not zero. That's why you have the commutator of the matrix uh, uh, bracket S comma T. Also, if you get the transpose of the product, this is just the reverse order product of the transpose. So this is the product of two matrices S and P. So this is just equal to the product of the transpose in reverse order. And the same goes for the Hermitian. This is the rule is the same for the Hermitian transpose. For unit matrix, the unit matrix is represented by the matrix 1, where all the elements in the diagonal is 1, and the rest, or the other elements, is equal to 0. You have this transformation. If you multiply that to another matrix, another n by n matrix, that gives you the same matrix as the original. So that's kind of a property that what is that property? The existence of an identity matrix. That when you multiply that matrix to another matrix, it gives you the original matrix. This one can also be written as this, and because of this existence of this identity matrix, you can find now an inverse of the matrix, so that when you multiply the inverse of a matrix to the original matrix, that will give you an identity matrix. And by the way, not all matrices have have inverses. They don't. Not all matrices have inverses. Only some of the square by some of the square matrix have inverses. So in this one, you have in equation 3.56, you have the inverse of a matrix multiplied to the matrix, and is just equal to the matrix multiplied to its inverse equal to the identity matrix. How can you find the determinant of the matrix? The determinant of the matrix is just denoted by this det of t here. Um, the determinant is I know you know how to get the determinant. For example, if you have a 2 by 2 matrix, that's just the diagonal diagonal to the right. I mean diagonal coming from upper left to lower right minus diagonal coming from upper right to lower left for the 2 by 2 matrices. But for 3 by 3 matrices, the determinant would be um, using cofactors. So so for a 3 by 3 matrix, you have the first row, for example, you have the first element times a cofactor plus or plus the negative of the second element of the first row times its cofactor, and then the third element times the corresponding cofactor. I know you have done that before, so I think at least you have done determining matrices, determinant of matrices for at least 3 by 3 matrix. So you can find the inverse by using this formula. So the C, uh, the C there is the matrix of cofactors, but in the formula you have to find the transpose of the C. So this is the condition for the C or the cofactors. So a matrix without an inverse is said to be a singular matrix. It's a singular matrix. And another thing to note about matrices is that if you get the inverse of the product of two matrices, then it is just equal to the product of the inverses, but the order is changed. So here you have S times T, the inverse of S multiplied to T matrix. This is just equal to um, uh, T inverse multiplied to S inverse, not S inverse multiplied to T inverse. The order of S and T is reversed here. There's a condition here. There's a definition for a unitary matrix. A unitary matrix is a matrix that is equal to its Hermitian conjugate. Uh, its inverse is equal to the Hermitian conjugate of the matrix. So that is the meaning of unitary matrix. It's not the identity matrix. The identity matrix is another matrix that has all one in the diagonal. But unitary matrix is as a definition of this one. It's um, the Hermitian conjugate of the original matrix is just equal to the inverse um, of the of the original one. Most of the transformation, like for example, if you want to convert Cartesian coordinates into spherical coordinates, or the Cartesian coordinates to in cylindrical coordinates, most of these matrices have um, transpose equal to itself. So it's kind of a property of the matrix that tells you that um, the transformation is by doing some manipulations of the matrix. So we have learned so many things: transpose, Hermitian conjugate, complex conjugate, the inverse of the matrix. So you have to remember that. Um, so this is an important statement. Assuming that the basis is orthonormal. Orthonormal, again, I'd like to repeat that orthonormal means that the basis, for example, in the three-dimensional space, you have the basis ijk. Those are the elements in your space that can uh, that spans your space, meaning that any vector can be written in terms of that basis. So for example, in three-dimensional space, you have ijk, so you can write a vector as 3jk minus um, j plus 5k, for example. So all the vectors can be written in terms of ijk. And ijk are orthonormal because if you multiply I with I gives you 1, and if you dot product I with I gives you 1, j with j gives you 1, and k with k gives you 1, and j with k, if you dot them, gives you 0. The rest is 0, but to itself it's 1. So that's what you call as orthonormal basis. That's just for three-dimensional. But if you go if you go to a space where if you go to a space where the dimension is higher than 3, then that definition also is applicable. So this is the transformation of the old basis vectors ei on a different basis set. So of course, if you have this transformation, this one, this can be compactly written as this one. Um, for some Sij, the S there is the transformation of if you want to convert the old basis to the uh, new basis. Here, like you have an old uh, vector, old basis vector ei to a different uh, basis vector f. The f there are the different is a different um, coordinate system, for example. So if you want to convert, there exists uh, a transformation matrix that could give the transformation. So this is also a linear transformation. So the components um, the components can also be given by that, as the previous equation has told us. The here so the superscript indicates the basis. Now this is, in this case, the basis is f, and here the old basis is e. So you can just use that matrix to uh, transform the components of the vector with respect to the old basis to a different basis, in this case f. Or uh, 3.61 can be written in matrix form as this one. So So in so for example, in the old basis you have uh, the basis E represented by E1, and in the new basis E prime. So your E1 is transformed into an E1 prime by using this matrix. Um, this is just the same as this one here, that one. Um, if you now, if you look at 3.62, if you multiply, if you multiply s, if you multiply s inverse to AF, S inverse here, on this side S inverse, and then on this side S inverse, you will get AE equal to S inverse times AF. And if you put this to here, here, you will have you will have um, you will have TE S inverse. And so if you look at AF, uh, your AF prime here, AF prime will just be SE prime here, like this one here. And if you put this AE prime, uh, this one here, to here, you will have STE prime, but AE prime is equal to this, so that your TF is actually equal to this one. Because like this one, you can write this as AF. You can write this as AF prime is equal to TF A to the TF AF, so that this one is equal to TF prime, um, or this is equal to TF times A uh, AF, this one here, so that you can cancel AF, and then you will have this matrix, this product of the matrix. So uh, the TF here is is said to be similar to the TE here. TF is similar to TE. In general, two matrices T1 and T2 are said to be similar if this follows this rule. For some matrix S, some non-singular matrix S, the S here, you can it can be any matrix, arbitrary matrix, for as long as you know the matrix and its inverse. Then if you apply it to a matrix, it gives you another matrix. That, or those two matrices, are then a similar matrix. And the similar matrices actually represent the same linear transformation with respect to two different bases. In this case, the basis here of T is E, and here the basis is F. The basis, again, I'd like to repeat, those are the vectors, the unit vectors. Um, those are the unit vectors spanning the space. So, like for example, for 3 dimension, those vectors are just ijk. For 4 dimensional space, then they would be represented in different vectors, but again, they follow the same properties as those as that of the 3 dimensional vectors. So in higher dimensions, then you have to think similar to the 3 dimensional vector, so as and so as to understand what a basis is. So similar matrices uh, bi- uh, are those matrices that represents the same linear transformation with respect to two different bases. So here, if the first basis is orthonormal, the second would also be orthonormal if and only if the matrix is unitary. Here, this one. The basis here of T2 is orthonormal if and only if the basis in T1 is also orthonormal. But there's a condition that um, S would have to be unitary. So what is a unitary matrix? The unitary matrix is just defined as this one. If the inverse is just equal to the Hermitian conjugate of that matrix. So for any matrix that has an inverse equal to the Hermitian conjugate, that's a unitary matrix. So you can practice and with some matrix later. But of all the properties of the matrix, um, there are two quantities associated with the matrix uh, that are not changed. They remain constant, and these two are called the determinant and the trace. So please study how to get the determinant of a matrix, and of course the trace would just be easy. The trace would just be the sum of the diagonal elements of the matrix. So if you add the diagonal elements, that would be the trace of the matrix. The determinant you can get, uh, you have to study it. And now, this statement is just to show that the determinant of the matrix in the basis E and the basis F are the same. Uh, this is just the proof of that. And of course, the determinant, you just have to remember the determinant is constant in a matrix from one basis to another basis. And of course, the trace is also a constant. And it also has a property that the trace of the product of two matrices, is also the the trace of the product of the two matrices in the reverse order. So this is T1, T multiplied to T2. I mean T1 multiplied to T2, and this is T2 multiplied to T1. That's the trace there. So here, now problem, um, just to give you a practice, you have to answer problem 3.8 on your own, and also problem 3.9. You can add the matrix, you can multiply the matrix, find its commutator, the transpose, the complex conjugate, the Hermitian, the trace, the determinant, the inverse. So it's a practice for you. Problem 3.8 and 3.9. And of course, you can also do 3.10 if you want, 3.11, 3.12, 3.13, 14, and 15. So um, let's discuss these eigenvectors and eigenvalues in next meeting. Um, you will have to um, you will have to answer an assessment for this lecture. For now, I'm really sorry if you can see blinking of the slides on the video, because this is I don't know if this is something wrong with the streaming app, or with is something wrong with the, or is this something wrong with the the Adobe application. But I really don't have a clue yet. So please answer the assessment, because that will be one of the basis of your grades. And please tell others that um, it's important that you answer those assessment. So um, that's all for now. See you next meeting. Mr. Tokero, please inform your classmates about this.